8.2 Lesson 2 Integration by Parts. Objectives: 1. Apply the integration by parts formula to find integrals, as we did in Lesson 1. But sometimes you could have a problem where you apply the integration by parts formula, and when you rewrite your integral, you get something on the right side where you have a simpler integral than the one that you started with, but it's still not something that you can solve. It's still not something where you can find an antiderivative. So in that case, you may have to do objective 2. Try integration by parts again. And that's what we mean by repeatedly apply the integration by parts formula to find integrals as needed. And we want to continue practicing choosing u and dv appropriately by using the given guidelines. So we have the same vocabulary that we had in Lesson 1. We're learning integration by parts, and we're working with either indefinite integrals or definite integrals which have limits of integration. So we're looking for antiderivatives of the integrand, and if we have an indefinite integral, you need to add a constant of integration to your answer because you're looking for a family of antiderivatives for indefinite integrals. We want to begin this lesson by emphasizing that depending on the problem, you may or may not need to use integration by parts. So pause the video and try these two problems and then continue to see if you were able to do them. So here we have the solutions to the two problems, and let's take a look at them. We'll begin by looking at number 2. Number 2 can be done using integration by substitution. So it is not necessary for you to do integration by parts for number 2. So you know that if you have e to the u du, if you have the indefinite integral of e to the u du, your antiderivative would be e to the u plus c. So if you can rewrite the problem that you have here using a substitution so that it becomes this, then you can do the problem using integration by substitution. And you look at the exponent for the exponential function, which is x squared, and you let u be equal to x squared. Does this work out? In this problem, it does, because when you find the differential of u, the derivative of x squared is 2x, and then you multiply by the differential of x. And you see that you have 2x dx as a part of the original integrand. So now you're able to replace the 2x dx with du. And you're able to replace e to the x squared with e to the u because u is x squared. So now that you have this, you are able to find your antiderivative, which is just e to the u plus constant of integration. And then you go back to the original variable, which is x, by replacing u with x squared, and this is your final answer. Integration by parts was not necessary for number 2. For number 1, there does not appear to be a suitable substitution that will work. So we will try integration by parts. So to do integration by parts for number 1, we have to begin by choosing u and dv appropriately using the guidelines. So we want to choose u to be such so that its derivative is simpler than u. And of course, if you choose u to be x, the derivative of x is 1, which is simpler than x. So that would be something that we can try. So the rest of the integrand would be dv. So we let dv be e to the 2x dx, and we integrate to find v. So an antiderivative of e to the 2x with respect to x would be e to the 2x over 2. You can do this mentally. If you want to verify that this is correct, you can try taking the derivative here using the chain rule, and you'll get e to the 2x. So having done that, we're now ready to apply the integration by parts formula here. And to apply that, this is what we're going to do. We're going to do u times v, uv, so we have x times e to the 2x over 2 minus the indefinite integral of v du minus the indefinite integral of v du. Du is just dx. So we have v du would be e to the 2x over 2 times dx. So now we're over here, and the main thing is you want to see if what you have here is something that you know how to solve, and it is. So we're able to complete the problem. So you can factor out the constant factor of 1/2, and you know how to find an antiderivative of e to the 2x. In fact, we did it over here, so it's the same, and this is what we have, e to the 2x over 2. And you can multiply the 1/2 and the 1/2 to get 1/4, and this is the final answer. So number 1, the indefinite integral of x times e to the 2x dx is equal to x times e to the 2x, all of that over 2, minus 1/4 times e to the 2x plus c. Now we'd like to take a look at an example in which we're going to repeatedly apply the integration by parts formula to find integrals as needed. So we begin this problem and we look at the integrand, and there is no obvious u substitution that would help us. So now we think the integrand is a product, so perhaps we can try integration by parts. So now you've got to refer to the guidelines for choosing u and dv. Guideline 2. Try letting u be the portion of the integrand whose derivative is a function simpler than u. So I'll try letting u be equal to x squared because the derivative of x squared is 2x, which is first degree, and that's simpler than x squared, which is second degree. So if u is equal to x squared, the remaining portion of the integrand will be dv. So now we will find du. Du is the differential of u. So you take the derivative of x squared, which is going to be 2x. So you have 2x dx. Now you need to find v. To find v, you integrate both sides of this equation here. So on the left side you have v, and on the right side the integral of sine is negative cosine. So we have negative cosine of x. The derivative of cosine of x is negative sine x, so you need to have the antiderivative here be negative cosine x, so that when you differentiate you'll get positive sine x. So now that we have that, we can go ahead and apply the integration by parts formula, and when we do that, this is what we have. So we write the original problem, x squared times sine x dx, and what is that equal to? uv minus the indefinite integral of v du. So we've got u v, so that gives us negative x squared cosine x minus the indefinite integral of v du. And v is negative cosine x, as you can see here. So we have negative cosine x. Du is right here, 2x dx. So I can write the 2 out front. 2x dx. So in fact I'll write 2x cosine x dx. And I can factor out this negative 1. When I factor it out, I have minus negative the integral of 2x cosine x dx, which is the same as adding. So we will have plus. So now we look at this, and the integral that we have here is still something that we cannot solve. We don't know what the antiderivative is. So we have not finished our problem, but we've made progress. because this does seem simpler than what we started with initially. Because we had x to the second power times sine x dx initially, and here we have 2 times x to the first power times cosine x dx. So what we're going to do is we're going to apply integration by parts once again on this integral. And if you want, before you apply the integration by parts formula once again, you could factor out the constant factor of 2. So you will have this. So now we're going to go ahead and apply the integration by parts formula again on x times cosine x dx. You would let u be equal to x. So let u be equal to x, and you would let dv be equal to cosine x dx. So the differential of u, the derivative of x is 1, so the differential of u would be dx, and you would integrate here to find v. So v would be sine x, because that's the antiderivative of cosine x with respect to x. So now we're able to use this to continue as follows. So I write all of this that we have here, and the part that we did integration by parts for is the part that I boxed in green earlier. So I have to now multiply all of that by this factor of 2, because 2 is multiplying that integral. So now I have, and I'll write this in maybe green, so I have uv minus the indefinite integral of v du. Again, I'm applying integration by parts to this indefinite integral. So uv, u times v would be x times sine x, uv minus the indefinite integral of v du. And again, v is sine x and du is dx. So v du would be sine x dx. And this is good because I know what the antiderivative of sine is. So I can complete my problem now. The antiderivative of sine is negative cosine, so I have minus negative cosine, which is plus cosine x, and then I have plus my constant of integration. And if you would like, you can take this 2 and distribute it to the 2 terms that you have, and if you choose to do that, your answer will be 2x sine x plus 2 times cosine x. And then you have the plus c. So here's an example of a problem in which we had to apply integration by parts twice to find our antiderivative. Integration by parts can also be used to solve problems such as this one here, where we have the indefinite integral of natural log of x dx. Up to now, we don't know how to find an antiderivative here. We do know how to find the derivative of natural log of x, but we don't know how to find the integral of natural log of x. The derivative of natural log of x is, of course, 1 over x. So how can we find the integral of natural log of x dx? We can use integration by parts. So let's look at the guidelines here. The guidelines say, try letting u be the portion of the integrand whose derivative is a function simpler than u. Then dv will be the remaining factors of the integrand. Of course, it would not make sense for us to let dv be equal to natural log of x dx, because then we'd have the same problem that we have here. So we would let u be equal to natural log of x, and what would be left? Dx would be left. So we would let dv be equal to dx. So when we do that, what happens? So we let u be equal to the natural log of x, and the differential of u would be the derivative of natural log of x, which is 1 over x, times the differential of x. And 1 over x is simpler than natural log of x. So now we have the differential of u is 1 over x dx. dv is dx, so to find v, we integrate both sides. So we get v is equal to x. So now that we have this, we're going to apply the integration by parts formula to our problem, which is the indefinite integral of natural log of x dx. And what would that give us? So the integration by parts formula says uv minus the indefinite integral of v du. So uv would be natural log of x times x, uv. I can write that as x times natural log of x, minus the indefinite integral of v du. So we've got v is x and du is 1 over x dx. So v du would be x times 1 over x dx. And of course, when you do x times 1 over x, you'll get 1. So x times 1 over x will simplify to give you 1, so you just have 1 dx here. So now this is x natural log of x, and this is something that we know how to find an antiderivative of. It's very easy. The antiderivative would be just x. So I have minus x. The derivative of x with respect to x is 1, so that's our antiderivative for 1. And then we have plus our constant of integration, and we've done our problem. Now if you wanted to check to see that this is correct, what can you do? With any integration problem, you can check your work by taking the derivative of your antiderivative. And if you have the correct antiderivative, you should get the integrand. So here's our check. We take our antiderivative here, and we try to find the derivative of it. So first, for this term, I can use the product rule, and this is what I would have for the derivative. For the second term, the derivative would be minus 1. And for the constant, the derivative would be 0. And when I simplify it, I have x times 1 over x is 1. 1 minus 1 is 0. So I have 0 plus 0, which is 0, and I have just natural log of x. And that is, of course, my integrand. So we have done this correctly. We're going to take a look at another example that's similar to this. So let's take a look at that. So in this problem, we want to find the indefinite integral of arcsine of x dx. We actually know how to find the derivative of arcsine, so naturally we're going to let u be the portion of the integrand whose derivative is a function simpler than u. In this case, just because we know how to find the derivative, that would seem to be the logical choice. So if we let u be the arcsine of x, the remaining portion of the integrand would be dv. So dv would be dx. So now the next step is to find the differential of u. The differential of u is the derivative of arcsine of x multiplied by the differential of x, which is dx. And the derivative of arcsine of x is 1 over the square root of 1 minus x squared. So that's something that you learned in Calculus AB. So we just take that differentiation rule and apply it here. And then we multiply by the differential of x. So now to find v, you're going to write this. You're going to integrate both sides here. So v is equal to the indefinite integral of 1 dx, which is x. So now we're ready to apply the integration by parts formula to rewrite our problem. So we have arcsine of x dx is equal to uv So u is arc sine of x, and v is x. So uv would be x times arc sine of x, uv minus the indefinite integral of v du. So here's v, and here's du, v du. So now we have x over the square root of 1 minus x squared dx. So we get this, and we have this indefinite integral here. Do we know how to solve this? And the answer is yes. We can do this by using integration by substitution. And in fact, you've already done this at the beginning of the day 1 lesson for section 8.2. So we'll take a look at the work from the activity at the beginning of the day 1 lesson, or lesson 1, 8.2. So you can see that we've already done that problem. We used integration by substitution, and we let u be equal to 1 minus x squared, then the differential of u. This is integration by substitution, not integration by parts. So the differential of u du is negative 2x dx. So x dx is du over negative 2. Here we do our change of variables step. We factor out the negative 1/2. We rewrite the integrand, and we apply the power rule for integration, and we go back to x. And here's our antiderivative. So now we'll take that antiderivative and apply it to rewrite this indefinite integral as negative square root of 1 minus x squared. So we have negative square root of 1 minus x squared, and then we have the constant of integration plus c. And of course, you have minus negative, which you can write as plus. So we're going to have plus the square root of 1 minus x squared plus the constant of integration c. So this is our final answer. So today we looked at lesson 2 of 8.2. We began by repeatedly applying the integration by parts formula to find integrals as needed. And then we looked at a couple of applications of integration by parts to problems such as the indefinite integral of natural log of x dx, or the indefinite integral of arc sine of x dx.